16.3, we talk about the fundamental theme for line integral. Now, first of all, remember the fundamental theme of calculus, right? So when you integrate this rate of change, and you will get the net change right here. So you integrate the derivative t, and then you just get fb here minus f of a, okay? So we call that the net change theme. So this one here is rate of change. Remember, think about the derivative as rate of change. And then what happened over here is this is the net change. So from A to B, how much the function value change, net change. So the way that I remember it, so the integral of the rate of change is equal to net change, okay? Now when you have a function of two or more variables, then you can think about the gradient actually play a similar role as this, the derivative of the function in this one-dimensional case, okay? The gradient here kind of plays a role like that. And then we have this theme over here, okay? When you integrate the gradient here over this curve, and this curve here is a smooth curve, okay? Just think about it, something like that. Has no corner, no sharp turn, and no break, okay? A smooth curve like this. Right now, the curve that we encounter, most of them are smooth curve, so we don't need to worry too much about that. And the C here is a smooth curve given by this vector function RT. Remember the tip of this vector R, think about that. The tip of the vector R is going to chase out the curve, okay, like that. And then we let this function, the small f function here, be a differentiable function of two or three variables, okay, with this gradient vector. And the gradient vector here is continuous on this curve C. Then the integral of this gradient over this curve is equal to the small f function, the function value at RB, which is at the end of the curve. This is the vector that is going to, at the origin, and point to this one, okay? Point to the ending, okay, RB, okay? This is a vector that point to that. So it's a function value at that vector, subtracting function value at the vector that correspond to the beginning of the curve, like that. So they're very similar, right? You're looking at this, right? This is the end function value, subtract the beginning function value. This is the function value at the end of the curve, okay? And then subtract the function value at the beginning of the curve, like this. So get this kind of play the role like this, okay? Note that we can evaluate the line integral of a conservative vector field. So what do you mean a conservative vector field? I'm going to give you a page here to go over what does it mean a conservative vector field, okay? So I'm going to ask someone to read this.
A vector field F is called a conservative vector field if it is the gradient of some scalar function, that is, if there exists a function f such that f equal to a potential function.
Okay.
In this situation, f is called a potential function of a f.
Okay, good. Thank you.
You're welcome.
All right. So if you can express this big F function as the gradient of some function, okay, or some scalar function, then they are related, okay, this way. Then this big F function is called a conservative vector function, a vector field, okay? So you might wonder what the name here come from. We will know about that. It has something to do with the conservation of energy. Okay, and then this small f function here is called a potential function for this big F. Before we talk about derivative, right, and antiderivative, but now we talk about conservative vector function, right, a conservative vector field. And then this is called potential function. Okay? It's kind of like duality, anti-duality. Okay, something like that. So here's some example. So I have this small f function here, the scalar function in two variables. And I can find the gradient of this by taking partial derivative with respect to x and partial derivative with respect to y. And then I get this function right here. This is the gradient function of that. And then this one over here, if I let big F to be this, then this big F here is a conservative vector field. So as long as you can find a function that you take the gradient is equal to that function, this big F function, then that big F function is called a conservative vector field. Okay, and this original function you have here, this small f function, is the potential function. And not all vector fields are conservative, but in physics we have a lot of it comes up a lot. Conservative vector field comes up a lot. Okay, for example, the gravitational field is actually a conservative vector field. I put it in here just for your information. If the small f function is equal to m times m times this, okay, then the gradient of this is equal to this. We did the calculation. And if you let the big F function to be this gradient of this F, then this big F function is a conservative. It's a conservative vector field because it is a gradient of some scalar function right there, right? And this called the gravitational field. Now, just briefly talk about what this here is, the physics behind this. So you have two objects. Each object, one of them has mass small m, the other one has mass big M. Then they will attract each other. The attraction between them, the force between them, is going to be given by F equal to G small m times big M divided by R squared. So the longer the distance between them, then the smaller the force, attracting force right there. And it is inverse proportional to the R squared, the force. And then proportional to the small m and proportional to the big M. The G here is the universal gravitational constant as given by this number. So that's how this formula here comes from. If you want to get more detail, I actually put a side note here, 1 and 2 below, which is the 2 pages, side note 1 and side note 2, for your information. So now we know what is a conservative vector field. So basically, a conservative vector field is one that you can express as a gradient of some function, small function f. So it's a gradient vector field of the small f right there. Now, if we have there's a lot of new information, new concept. It could take a while to sink in. Okay, think about it. So, what is the theme that we just talk about? The one that we just talk about here, this theme over here, kind of like the Lagrange theme. This theme over here says that the line integral of this conservative vector over the curve C is the Lagrange in F. Okay, so this part over here, this is the Lagrange in F, and at the endpoint of C. Okay, so this part over here, this is at the endpoint of C, the endpoint of C. Then. So let's say that one more time. So the line integral of this conservative vector field over this curve C is equal to the Lagrange of this small f function, Lagrange in this small f function, the potential function f at the endpoint of the curve right here. Okay. So let's think about in two-dimensional case, like in R2. So if we integrate the gradient along the curve C, okay, then you just get f of at this end over here, see the curve starting at x1, y1 and ending at x2, y2. Then it is equal to the small f function, the potential function, evaluate at x2, y2. subtracting this function, the small f function, evaluate at x1, y1. So that's really neat, isn't it? It seems like it's so much simpler, providing that this is a conservative vector field, which means it's a gradient. Okay. So then when we look at this, then we say, only the endpoint here matter, right? So it doesn't matter which way I go. I can go different way. As long as I start from this and end it at this, I can have different curve. Then if I integrate this gradient over different curve that have the same starting point and ending point, according to this theme, I should get the same result because it's the leg change of the function at the end point, right? Right here. Okay. So that's something very interesting. Now in 3D, in R3, it's similar. When you integrate the gradient, then this part that's over the curve C, that's equal to the lecture function between this end and this end. Okay, only the endpoint here matters. Okay, and I actually include a proof for this right here. So when we integrate this gradient over this curve C, well, how do we do this integral? Well, we just talk about how do we do integral in 16.2, right? So this is the force, right? Think about that as the vector field. So it's a vector field, and then the dr over here, is r prime of t dt. And from this step to this step, we want to express everything in terms of t. Okay, so the gradient factor here, the gradient over here, you want to express this as a function of t, and this, okay, this is also a function of t. Okay, so the gradient of the function is basically just this one, this, and this, right? It's going to be, that one is going to be the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, has 3 components. Now remember, this is the dot product, right? The dot product. So when you dot it with, we dot it with r prime. So what's r prime? R prime t. R prime t is dx dt, right? And then dy dt, and then dz dt. So this is r prime of t, this vector. Okay. So when you dot it with this, then you have this multiplied with this. This is what you got over here. Okay. And then this times this, that's what you got from the middle term here. And then plus this one times this is what you got over here. Okay, so that's how we do that product. And now, looking at this we might as a chain rule. So when you get x, y, and z, and then x, y, and z are function of t. So when you try to find the duality of this f with respect to t, then you have partial derivative f with respect to x times dx dt plus partial derivative f with respect to y times dy dt partial derivative f with respect to z times dz dt, which is exactly what we have here. So this whole thing here is actually the duality of this f here, this function f, with respect to t. So by the chain rule, okay? Now, when you have this, so when you differentiate this with respect to t, and later integrate with respect to t, by the fundamental theorem of calculus, okay, that's equal to this function f, evaluate at r of, now you put the b here again, r of b, and then f evaluate at r of a. That was the fundamental theorem of calculus. So it's actually not too bad to prove it, so not too long. So now you prove it, you just need to remember the result, okay? The result here is this one. So you should actually maybe highlight that. Okay, that was a very important result. It's a very neat result also, okay? So kind of like the Lachine theorem like that, when this is a gradient, okay? All right, so after this, and maybe I ask someone to read this. When do we use this? Okay, can I ask someone to read?
A cell phone manufacturer can use the fundamental theorem for line integrals to determine the amount of kinetic energy your cell phone will have if you drop it from a certain height.
They test the durability of your phone.
Yeah, they want to test the durability of the phone. Yeah, you got it. Okay. The second paragraph right here.
Okay. A NASA physicist planning to launch a satellite from the surface of the Earth into low Earth orbit can use the fundamental theorem for line integrals to find the work done by gravity on this satellite in order to determine how much fuel will be necessary for the rocket carrying the satellite to complete its mission.
Okay, very good. Okay, the last paragraph I'm going to.
A hydroelectrical engineer can use the fundamental theorem for line integrals to find the amount of kinetic energy a waterfall will have at the bottom of the waterfall in order to determine how much electricity can be produced from this waterfall.
Okay, very cool. Learn something new. Okay, good. All right. So, okay, let's just do this one example here. Okay. So today I will just go whatever I can go, and then I will make a video to finish up. I don't want to take too much time. So that's maybe we just finish this up. Okay. So find the work done by the gravitational field. So this is the gravitational field that we just talked about. In moving a particle with mass m from this point to this point along a piecewise smooth curve C. Well, at first you think it might be so difficult, right? Actually, because the theme that we have, okay, that actually make it easier. Okay, this gravitational field is a conservative vector field. We just talked about that. That means it is a gradient of some function. That gravitational field is actually the gradient of this function. If you take the gradient of this function, okay, and we do the calculation before already, we actually prove it already, then you will get this gravitational field over here. So if I try to find the work done, move a particle with mass m from this point to this point, so all we have to know, because this one here, it is a conservative vector field, so it can be expressed as a gradient of this small f. All we need to know is the end point. So the end point. Okay, so we're given the two end, right, from this point to this point. And you get the result, right? It doesn't matter the curve go which way. As long as you have this two end, it will go like this. Now we're going to talk about independence of path. Suppose we have two curves, two piecewise smooth curves, C1 and C2, and we call them path. They have the same initial point A and the same terminal point B. From an example we have done before, we know that in general, the integral over the curve C1 and the integral over the curve C2 are not equal. For example, in 16.2, example 4, we integrate this function f along this curve C1 and C2. C1 and C2 have the same initial point and terminal point. The integral of this function f along this curve C1 is equal to negative pi over 6. The integral of this function f along this curve C2 is equal to 40n pi over 6. So even though we have the same function and the two curves have the same initial and terminal point, when we integrate along different paths, different curves, then the result in general are not the same. But one implication of this theme over here is that the integral of the gradient of small f function along different paths will be equal to each other as long as the path have the same initial point and terminal point. And whenever this gradient of f is continuous. In other words, the line integral of a conservative vector field depends only on the initial point and terminal point of a curve. So if the big F function is a continuous vector field, then you can write it as the gradient of small f. And if that vector field has domain D, then inside the domain D, we can integrate this function along different paths. And the result of this integral along different paths are equal as long as the path have the same initial and terminal point. So remember, what do we mean a conservative vector field? If big F is a conservative vector field, that means it can be written as the gradient of a scalar function small f over here. So if you can write that as a gradient of small f, then this big F over here is a conservative vector field. So what does this one here mean? So this equation here just show that line integral, this is a line integral over here, of conservative vector field, which means it can be written as a gradient of a scalar function f. Then line integral of conservative vector field are independent of path. So if you go this path or this path, it really doesn't matter. The result will be equal because they have the same initial and terminal points. Now, let's introduce another definition. It's called closed. So here is an example of a closed curve. So a closed curve is defined to be a curve that its terminal point coincide with its initial point. So if you start here, then you're going to end it over here at the same point. So when we do the line integral of this big F function, which is the big F here is a conservative vector field, then when you do this line integral here, it is independent of path inside the domain of this big F right here. So imagine that this is the domain of this big F function, and if you have a closed curve that's inside the domain, then when you integrate this big F function along this closed curve, then what happened? What do you think about the result? Well, what we do over here is we can choose two points on the curve, say A and B. So when you integrate this big F function from A to B, that's called C1 right here. And then afterward, you're going to add from B to A to return to this same point. So this is C2. So adding the integral of this big F function integrated over C2. At the integral along this curve C1 and along this curve C2, what happened here is the sum of them will be equal to 0. So when you have a closed curve inside the domain of this big F function, when you integrate along this closed curve, this total integral will be equal to 0. We have this theme here. The line integral of this function f is independent of path in D, even only if the integral of the function along any closed path C is equal to 0. This closed path C has to be inside the domain of the function f. So if you integrate the function over any closed path C that's inside the domain of the function, if you get that equal to 0, then we'll say that the line integral of this big F function is independent path inside the domain. So providing that the vector field here is a conservative vector field, such as the gravitational vector field, then when we integrate over any closed path, the result should be equal to 0. For example, when we integrate this gravitational force field, so if you try to find the work done by moving the object, for example, maybe from here to here, here, and here, and you end up at the same point, then the total work done by this gravitational force field will be equal to 0. Next, let's talk about another concept here, which is an open set. So here an example of an open set D in R2. Notice that D here doesn't contain any boundary point of the set. So for every point inside this D, let's just say I'm going to pick, say, this point over here. Then you can always draw a disk with center at this point, and this disk is going to be entirely inside this D. So, well, you say, well, if it's close to this boundary here, you can make the radius of the disk to be small enough, and the disk will be still contained entirely inside this set D. So as long as the D doesn't contain any of its boundary point, then we can draw a disk for any point inside this D that will be entirely inside this set D. And this kind of set, we call that an open set D. So D doesn't contain any of its boundary point. Another concept here is connected, a connected set. So a connected set, here's an example of a connected set. So D here is connected. Well, you can see that it's not broken into two or more pieces, right? The formal definition for connected set is that for any 2 points in D, say I have this point here in D and this point here in D, then they can be drawn by a path that lie entirely inside this set D. Then it is a connected set. So here we have an open set D and a connected set D. So open means it doesn't contain any of its boundary connected, then any 2 points inside D, you can find the path that is contained entirely inside D. Now, this set D over here is not connected because if you have a point here and point here, then you can't find a path go from this point to this point that lie entirely inside the set. We have at least some part of the path is going to be lie in outside the set, right? So this is not connected. Now we have a theme. Suppose F is a vector field that is continuous on an open connected region D, then the line integral of this function F over the curve C is independent of path inside inside D, where this F here is a conservative vector field, which means that you can write this as a gradient of a scalar function small f. So this line integral is independent of path. What does it mean here is if you integrate the function f over here along any path inside this region D, then what it really matters is the initial and terminal point. The path that goes from A to B doesn't matter. As long as you have the same initial and terminal point, this line integral here will have the same result. So that's why it's called independent of path. So which is a very good, very useful and very neat result to have. So if we integrate this function f inside this D along any curve C, all we care about is the function value f, small f, at this initial and terminal point. So that's a very useful and powerful thing. So the question here is, how can we know this big F function is conservative? In other words, how can we know this big F function can be written as the gradient of a scalar function small f? Well, if the big F function is equal to the gradient of the small f function, if this is in R2, so we can write big F as Pi plus Qj, where P and Q has continued first order partial derivative. So what does it mean? That means if you take partial derivative of P and Q, then the partial derivative will be continuous. Then if the big F function is the gradient of F, then the small p here is the partial derivative of the small f function with respect to x. Q is the partial derivative of small f with respect to y. Now, if we take this p here and differentiate that with respect to y, then we get the second partial derivative, big F function. Okay, first with respect to x, then with respect to y. Then by Clairvaux theme, that is equal to the second partial derivative function, small f, first with respect to y, then with respect to x. Remember, these two are equal by this theme. Now, this one over here is exactly equal to this function, differentiate that with respect to x. So these two are equal. So now we have a theme. If big F is equal to Pi plus Qj, is a conservative vector field, and P and Q have continuous first partial derivative on a domain D, then throughout the domain D, we have the partial derivative of P with respect to Y is equal to the partial derivative Q with respect to X. So for a conservative vector field F, if you take the partial derivative of this first component with respect to Y, and you take the partial derivative of this second component here with respect to X, the result will be equal. This is for any conservative vector field where P and Q have continuous first order partial derivative, which means when you take partial derivative of P and Q, then they will be continuous. Next, we're going to introduce another concept called simple curve. So what do you mean simple curve? Here, this is an example of a simple curve. This is also a simple curve. The definition for simple curve here is a curve that doesn't intersect itself. So for example, this curve over here intersects itself, so that's not simple. This curve here doesn't intersect itself, it's simple. So this is actually a closed curve, right? Close. But it's not considered intersecting. Okay. So this is a simple and closed curve. This curve is not simple because it intersects itself. Okay. It is closed. So you take any point, you can go back and go back to the same point over here when you move along the curve. Another concept is a simply connected region. Here's an example of a simply connected region. So remember, connected means if you pick any point inside the region, then they can be drawn by a path that's entirely inside the region. So this is a simply connected region. It is a connected region. Now, these three examples here are not simply connected. So what does it mean simply? A simply connected region over here in R2 is a connected region. First, it has to be connected. And what else we need? We need every simple closed curve. So if you take any closed curve over here, then inside this closed curve, those points are all inside the region. Take any simple closed curve, then inside this curve, that region, every point inside that region will be entirely inside this D. Now here is not a simply connected region because if you draw a curve, a closed curve like this, then inside this closed curve, you see the white part over here? Those points are not inside this set D, and similar for this one. Now this region here is not simply connected because it is not connected because if you draw, you can go from this point to this point by any path that's not entirely inside the set. Some part of the path has to be outside the set. So this is a simply connected region, and these three are not simply connected. Now, after this concept, we can talk about this theme here. This is kind of like the converse of the theme that we just had. Last time we talked about if this big F function is a conservative vector field, which means that the big F can be written as the gradient of some scalar function F. And if this P and Q, they have continuous first order partial derivative, then take the partial derivative p with respect to y, and take the partial derivative q with respect to x, these two results are equal. Now, conversely, if we have this, now can we say this big F function is conservative? So this theme says that is true when big F is on an openly simply connected region D. So the converse of that theme is true, which means if you have the partial derivative of p with respect to y equal partial derivative q with respect to x, then this big F function is a conservative vector field, providing that the D over here is an open, so it doesn't contain any of its boundary, and simply connected also, which means it doesn't have any hole in it and it's not broken into two or more parts. Then this big F function will be conservative. So if this partial derivative p with respect to y is equal to partial derivative q with respect to x throughout this region D, which is an open, which means it doesn't contain any of its boundary, simply connected also, which means it doesn't have any hole in it and it's not broken into separate pieces, then we will have this big F here to be conservative, which means it can be written as the gradient of small f, where f is a scalar function. Now let's do some example. We want to see if this vector field is conservative. So we're going to use the theme that we stated above right here. We're going to take the partial derivative of this first component here with respect to y, and take the partial derivative of the second component here with respect to x, and see if they're equal. So take the partial derivative of p here with respect to y, we got -1. Take the partial derivative of this with respect to x, we got 1, and they're not equal. So when they're not equal, then certainly the big F function is not conservative by this theme phi over here, because if it's conservative, they should be equal. If they're not equal, certainly is not conservative. So these two being equal is actually a necessary condition for this big F here to be conservative. If we violated this condition, then the big F here certainly is not conservative. Next example, we want to determine whether this vector field is conservative. Well, just like before, we're going to take the partial derivative of this function with respect to y, and then take the partial derivative of this function with respect to x. And in this case, it turned out to be equal. Both are equal to 2x. Now, if they're equal, we also need to see if the domain of this f over here is it open and simply connected, right? The domain of this big F function is this entire plane R2. This entire plane is open. It doesn't have a boundary, and it is simply connected. So it doesn't have any hole in it, and it's not separate into two or more pieces. So the domain for this big F is an open and simply connected set. And we also have this condition satisfied. So by the theme that we just stated above, this big F function is conservative. which means that it can be written as the gradient of a small f. Now the next question here is, suppose I know this big F is conservative, then how do we find the small f function? So then I can write the big F as the gradient of this small f function here. Now we can use partial integration to find the small f function. Let's look at this example. So this is the big F function, and we're trying to find this small f function such that big F is equal to the gradient of the small f here. Now, how do we do that? So we are given big F is equal to this, and we know big F is conservative. So we're trying to find the small f, so then big F is equal to the gradient of small f. So big F is equal to gradient small f means when you take the partial derivative of small f with respect to x, that will be this first component function of the big F. When you take the partial derivative of small f with respect to y, you get the second component of this big F function. Now, we're going to integrate this. So we're going to integrate this with respect to x. Antiderivative this with respect to x is 3x. Antiderivative this with respect to 2xy is x squared y. And we should add a constant function with respect to x, which means a function that has no x involved. So instead of putting a constant, say c, over here, we should put a function, g of y. It's a function of y. It has no x involved. So this is regarding as a constant function with respect to x. So that's something you should pay attention to. Okay? Instead of putting a constant c, we put g of y. Now the next step over here, we're going to use this information and use this information. So we're going to differentiate this function, take the partial derivative of this with respect to y, so that we can compare with this partial derivative with respect to y, so that we can figure out what this g of y is equal to. So take the partial derivative of this with respect to y. The derivative of 3x with respect to y is 0. The derivative x squared y with respect to y is x squared. The derivative gy with respect to y is g pi of y. Now, this one and this one both are partial derivative of the small f with respect to y. So comparing them, we know that g pi of y is equal to negative 3y squared. Now, once you have this equation, we're going to integrate both sides with respect to y. Antiderivative this with respect to y is negative y cubed. Now we add a constant because this is a function of y only. So there's no x here involved. So this is a function of one variable, y. So here is a constant k, a number. So now we figure this g of y is equal to, we can go back and substitute g of y equal to that and get this small f function. So we replace g of y by negative y cubed plus k. We got this small f function. The small f function is the potential function of the big F function, which means that the gradient of the small f is equal to big F. Part B. We're going to evaluate the line integral of this big F function over a curve C, and this curve C is given by this vector function where t goes from 0 to pi. From theme 2, because the curve over here is a smooth curve and the small f function the gradient is continuous. So by the theme 2 over here, all we have to know is the function value at the endpoint of C. Substituting t equal to 0 and t equal to pi, we get the two endpoints, 0, 1 and 0, e to the negative pi. And that's the curve. By theme 2, to evaluate the integral of the big F function over the curve C, we just need to find the function small f is valued at this two end of the curve. So we use the function value at the end point, which is this point here, subtract the function value of small f at this initial point here. So substituting x and y to be 0, 1 into this small f function. Notice that for this small f function, when you try to find the net change, when you subtract the function value at the two end, the k here is going to be subtract out. So let's make things simpler. Just think about the k is equal to 0. So we're going to make this k equal to 0, choose k equal to 0, and let f of xy equal to this function with the k equal to 0. So substituting the two endpoint in, the small f function at this terminal point, subtracting the small f function at the initial point, we got this result here. So this is the integral of the big F along this curve from this point to this point. Actually, as long as you have the same starting point and same ending point, it really doesn't matter what path do you take. The integral of the function along any path will stay the same as long as the path have the same initial and terminal point. Notice that using this theme, all we have to do is just subtracting the function value at the starting point and at the terminal point and the starting point. This method is much shorter than the straightforward method for evaluating the integral that we learned from 16.2. The example we just went over was the big F is a vector field on R2. In this example, the big F is a vector field in R3. We're trying to find its potential function small f. The process is very similar to the last example, finding potential function for vector field in R2. In this example, we're given a vector field in R3. We try to find its potential function, small f. If there is such a function, small f, then gradient of small f is equal to big F, which means the partial derivative of small f with respect to x, with respect to y, and with respect to z, those partial derivatives will correspond to the first, second, and third component function of the big F. Then we're going to take one of them, say the first one, first component, and this is the partial derivative of small f with respect to x. So we're going to integrate that with respect to x. Is equal to antiderivative y squared with respect to x is xy squared. Now, instead adding just a constant, this is a constant function with respect to x, which is a function that has no x involved. So this is regarding as a constant function with respect to x. So just like before, once we get this function, small f, we're going to take partial derivative with respect to y. So we get x times 2y, so you get 2xy. And the derivative of this with respect to y is the partial derivative of this with respect to y. And now we're going to compare this with the possibility of small f with respect to y that we got above. Comparing these two, this is equal to this. Now, once you have this is the possibility of g with respect to y. So when we integrate that with respect to y, we will get g of y and z is a function in y and z. And integrating this side with respect to y, we get y times e to the 3z plus a constant function with respect to y. This constant function, because this is a function in y and z, so this constant function with respect to y is a function that has no y involved, only has the z involved. So it's h of z. Once we figure out g of yz equal to this, we can substitute this back into here to get this function, small f. So this function small f is equal to xy squared plus y times e to the 3z plus hz. We still need to find out what this hz is equal to. To do that, we're going to differentiate this with respect to z because we want to compare that possibility with respect to z with what we got for the third component of the big F function, which is the possibility of small f with respect to z. So differentiate this with respect to z. So take the possibility of the small f function with respect to z. The derivative of this with respect to z is 0. The derivative of this with respect to z is y times 3 e to the 3z. The derivative of this with respect to z is h pi of z. Now we're going to compare this with this equation we got above. The possibility of small f with respect to z is 3y times e to the 3z. So compare this with this, we find out that h pi of z is equal to 0 because this is exactly equal to this. So h pi of z equals 0, which means that h of z is equal to a constant because this h of z is a function of one single variable z. And if the derivative of that equals 0, then it is a constant number. So h of z is equal to a constant. Now, finally, we know h of z here is a constant. H of z here is a constant. Then we can just replace this here by constant k. So we find this potential function f is equal to this. And you can verify this by taking partial derivative with respect to x, with respect to y, with respect to z, and see if the gradient of this small f is equal to the big F. So that's the end of 16.3. We learned a lot today. So what we have learned today, one important thing that we learned today is if C here is a smooth curve given by this vector function, and the small f is a differentiable function of 2 or 3 variables, whose gradient f is continuous on this curve C, then we can find this line integral by find the lag change of this function at the endpoint of C, which is an analog to the lag change theme we learned in calculus 1. And we also learned that the work done by a conservative force field, such as the gravitational force field, a conservative force field means that force field can be written as the gradient of a scalar function small f. So if it's a conservative force field, then the work done by the field, this conservative force field, for example, the gravitational force field, as it moves an object around a closed path is equal to Z if the path is a closed path. Number 3, we also learned that suppose the F is a vector field that's continuous on an open connected region D, then if the integral of big F over a curve C, if the line integral of big F is independent of path in D, which means that only the function value of the small f at the endpoint matter, then the big F function is a conservative vector field. And we can write this big F as the gradient of small f, providing that the function big F is continuous on an open connected region D. Open means it doesn't contain any of its boundary point. Connected, you can think about that, is not separate into different pieces. And we also learned that if this big F is defined by this P and Q in this way, it is a conservative vector field, which means it can be written as a gradient of small f. And where P and Q have continuous first order partial derivative on a domain D, then throughout the domain, we will have the partial derivative P with respect to Y is equal to the partial derivative Q with respect to X, providing that the F here is conservative, which means that if this is not satisfied, then automatically you can say that this big F is not conservative. Next, we learn about if the big F function is a vector field on an open and simply connected region D. Open means it doesn't contain any of its boundary. Simply connected means it doesn't have any hole in it and it's not separated into different pieces. So if F is a vector field on an open, simply connected region D like this, and suppose P and Q have continuous first order partial derivative, and the partial derivative P with respect to Y equal to partial derivative Q with respect to X throughout this region D, then we'll say we can conclude that the big F is conservative, which means it is equal to the gradient of a scalar function, small f. So one way to prove a vector field is not conservative is to prove that partial derivative P with respect to Y is not equal to partial derivative Q with respect to X, to show that this is not satisfied, which is what we have done in example 2. In the example we went over, so we show that the partial derivative of P with respect to Y is not equal to the partial derivative Q with respect to X. Therefore, this vector field is not conservative. Now, one way to prove a vector field is conservative is we first show that the partial derivative of P with respect to Y equal to partial derivative Q with respect to X throughout D. And then after that, we have to show the region D is open and simply connected. For example, here we show that partial derivative P with respect to Y is equal to possibility Q with respect to X. That's number one. And number two, we show that the domain for this vector field, which is R2, is open and simply connected. So it satisfies these two conditions, then this vector field here is conservative. And at last, we talk about how to find the potential function small f such that big F is equal to the gradient of small f. So we go back and look at example 4. So we're given this vector field. So we know that possibility small f with respect to x is this first function, and possibility of small f with respect to y is this second component function. Then what do we do here is we're going to integrate one of them. Usually take the first one and integrate that with respect to x, and you get a function or a family of function. And when we do that, this constant function is supposed to be a constant function with respect to this x. So since this is a function in x and y, so that will be a function in y only. And then after that, you're going to make use of this, compare with this. So to connect this one with this one, you're going to differentiate. You're going to find the partial derivative this with respect to y. So then you can compare this one with this one to figure out what the gy here is. So once you take the partial derivative this with respect to y, you compare the partial derivative over here and here. You know that g pi of y is equal to this. Then you can figure out what g of y here is equal to by taking antiderivative of this. Once you figure out g of y is equal to this, then you can just go ahead and plug it back in to find this big F function. So this is how to find the potential function small f in R2. And in R3, for a vector field in R3, the process is similar. How to evaluate the line integral of a conservative function over a smooth curve C given by RT t greater than equal to A less than equal to B? To do that, we'll use the Theorem 2 above. So we can just consider the function value of small f at the endpoint of the curve C. And we can find the net change in small f. All right, so this is for 16.3. We have learned a lot in this section, and there are so many new concepts. It will really take time to digest. And I hope by taking time to digest, to study, we'll feel more comfortable with this material.